Okay, this is our last section of the book, section 12.3. We're going to do this in 2 days. So this is the first day. We're going to do, I believe, an interval here. So inference for slope. This is kind of a strange one. Just to be honest, it's a little bit different. So scatter plots of the duration of interval between eruptions of Old Faithful of all 263 eruptions in a single month. The population least squares regression line is shown in blue. So we see that the duration of the eruption, the interval until next eruption changes. Kind of an interesting graph. Okay, a regression line is called a population regression line, the true regression line. If that's the case, we're going to use all the Greek letters there. We're going to use, mu of y equals a plus bx. We're talking about the population regression line. So if you're talking about the sample, which is usually what we're drawing, it's going to be y hat, the predicted y value of a plus bx. Instead of using alpha and beta there, we're using not Greek letters because it's not describing the population. What's weird is, if you're not used to this, it's not mx plus b. So a is the y-intercept and b is the slope. So we always think of, we use different notation than we do in Algebra 1. So we don't call it mx plus b, we say a plus bx. We're starting with the y-intercept, and then we kind of go up from there, essentially. Here are the plots. The least squares regression line in green for 3 different sample random samples of 15 eruptions. The population graph is in blue, so that's the true regression line. If you take samples, those aren't going to match the line. In fact, sometimes the slope is a little bit more, sometimes the slope is a little bit less. You're going to get many, many different slopes if you take samples of a certain size. And so you can't expect the slopes to exactly match there. It's going to be a little bit different each time. Yeah, look at those slopes. I mean, they varied. It's supposed to be 13.29, and they were as low as 10, as big as 15.7. I think they did actually like a simulation here, and they came up with all of these possible slopes. We see 13.29s in the middle. It does look like it's an unbiased estimator if that's the case, but you can see it, and it looks approximately normal, but they're spread out all the way to a slope of 18 to a slope of close to 8 there, so big difference there. Shape is approximately normal. The center is the exact value of the population slope, so we're trying to measure the slope here. Variability is a new equation. You haven't seen this one before, so this is for slope standard deviation. So when you take the standard deviation of the population divided by the standard deviation of the sample times square root of n there in the denominator, and you get 1.42 for this one if you did that. We'll do that example in a minute. We'll do one. Choose a simple random sample. What is the sampling distribution? So you want to talk about the mean of the sampling distribution, which is beta, the standard deviation, which again, we just went over that formula, and then the sampling distribution of B is approximately normal. Those are the things we're looking for there to describe that. Very strange looking graph here. So this is, it looks like 3 different samples. That red line that goes through, runs through all 3 is the kind of regression line there of the population for the slope. So it's the measurement of slope there. So these are the conditions for regression inference. If you can remember LINER, that's the abbreviation or acronym there. So if we're doing, we're talking about slopes here. So the linear means the relationship x and y has to be linear, right? We know that one. Independent. Oftentimes we have to check the less than 10% condition here to check independence. Normal, it should look approximately normal. Equal standard deviations. I need to show this with a picture in a minute, but all the values are kind of equally above and below the line on the residual plot. The data comes from a simple random sample. So again, it's always true. If you want to make inferences about this, you pretty much need a random sample or random assignment fit experiment. Here's an example of linear and nonlinear. So you can see on the left, that graph looks linear. On the right, It does not look linear. It looks like a curved graph, and so that would not be, that's talking about the residual plot there. If the residual plot shows a curved pattern, that's not good, right? So it's not linear. I'll check the conditions for my, let's examine the scatter plot to see if the overall pattern is roughly linear. To make sure there are no leftover curved patterns, always look at the residual plot. That can be good to do. Okay, independent. So typically we're going to check the less than 10% condition for that one. Normal, again, we want to look at the plot, make sure that it looks approximately normal. This one we want to look for, this is probably the weirdest one, the weirdest thing to check. You look at the residual plot, you can see that y=0 line right there that goes in the middle. You can see both of these, it looks like the activity above the line and below line kind of mimic each other. There's, on the first graph, there's 2 points to the right and 2 points down below on the right. They are in similar spots. You can see that it almost looks like a reflection. It doesn't have to be a perfect reflection, just approximately. So it looks somewhat symmetric with the residual line y=0 there. Random, I should say something about a random sample. Okay, so this is the problem we have for today. Now, this is just one example for this. Mrs. Baird's class did a fun experiment using paper helicopters. After making 70 helicopters using the same template, so they should be the same or close to it, students assigned 14 helicopters to each of the 5 drop heights. So they had those different drop heights. Teams of students released 70 helicopters in a random order and measured the flight time in seconds. The class used computer software to carry out the least square regression analysis. Here's a scatter plot of the different, here's a scatter plot, the residual plot, and a histogram of the residuals. So these are all of the residuals here. So check whether the conditions are true. So the first condition is linear, and that first graph, it does look linear there, and the residual plot seems to be somewhat symmetric. There's no leftover curve pattern in the residual plot, so that's okay. Because they were released in random order, no helicopter was used twice. That seems to be independent of each other. So we didn't have to check the 10% condition in this case. The next one is normal. You can see that the residual looks approximately normal. That looks good. You also want to check the equal standard deviation. So that's that middle plot of residuals. The residual plot it does look somewhat symmetric around the line y=0 there. So it does kind of look symmetric. So I think that passes that test. Finally, it says that they were randomly assigned to the different drop heights. So that's all good. Yeah, we're not looking for perfection here. It doesn't have to be perfectly normal, just approximately normal, somewhat equal in the standard deviation. When the conditions are met, we can do inference, okay? So this is our formula that we're trying to get to, but we use that one. A estimates alpha, B estimates beta, and S estimates sigma there, which is the population standard deviation. This is our formula for the standard deviation of the slope. We actually don't use this in our interval, though. I'll show you what we use in our interval. We use the standard error, actually. So this is the part of our formula for the interval. It is on your formula sheet. It's called the standard error of the slope. So B is the slope. Remember that? So it says SE of B, standard error of the slope. Standard error is typically how far the sample slope typically varies from the population slope. So we just multiply by, instead of square root of n, it's square root of n minus 1. It works out better that way. Okay, so what is the estimate for A here? So you can see on this line right there where my cursor is, A is going to be, it's next to the word constant. That's where the y-intercept is located. So it says negative 0.0371. So, what is the estimate for alpha? That's a weird thing to say because, in other words, if A is negative 0.0371, if a helicopter is dropped from 0 centimeters, it will take about negative some seconds to land. That just doesn't make sense in the context of the problem, that the y-intercept would start at a negative number. So in this case, the y-intercept doesn't really have a meaning. There's no way for the to take negative seconds to land. It just doesn't make sense. So what's the estimate for B? Right below the y-intercept is the slope. So you have that slope right there. If you think about slope as being rise over run, so slope is rise. So the slope, I guess we call that A plus B. So B, the slope is the number right below the y-intercept, which would be 0.005724. So the idea of this is that for each time so this is like drop height here, and this is the flight time. So if you think of this like a fraction, that's what you really want to think about. Every time the height changes by whatever the unit is here, whatever that, you usually say the unit on this, the time changes by 0.057. In fact, it increases by 0.0057. This is a positive slope. So the meaning is this: for each increase of 1 centimeters, because it was measured in centimeters in the drop height, the average flight time increases by 0.0057 seconds. So not a whole lot, but that's each centimeter, right? I mean, so that's going up just by centimeters. That's pretty small change. What's the estimate for standard deviation? So if you can find that under, so it's the number right there. Actually, it says S right there. Do you see where it says S right here at the bottom left? So that's your standard deviation. The actual flight times typically vary by about, remember that, by about 0.1681 seconds from the time predicted. Again, we're talking about a y hat here. We're predicting values using this regression line. Give the standard error for the slope. We could plug in the formula, but it actually says the standard error for the slope. If you look just to the right of the slope, so the slope is 0.0057. That number to the right of it, that's in the standard error coefficient column, that is the standard error of the slope. So it's 0.00020818. Usually in this section, they give us computer output. We don't usually even have to put it in our calculator. I'll talk about that in a minute, but not usual. So our formula is, again, we're going to do B, which is our slope, plus or minus the t critical value times the standard error of the slope. Okay, so you could do this in your calculator. Just for fun, I did type the data in my calculator. So I typed in all of those values. That's a lot. Go to menu. 6 would be interval. And it's called a ln-reg-t interval. I don't think you'll ever actually have to do this. There's two options, slope or response. We would do slope. We're doing slope here. Choose your, I think miles was our X there, and price was our Y. Assuming you're doing 95%, I'm just going to leave it like that. So it gives you all this data, which I think is the same data they're going to have in their output. Some students might do it just so that you have, it's easier to read the stuff. It actually is easier than reading pure output sometimes. But you can see that number, like you can see in the calculator, this is considered the slope, right? And you can see right next to miles driven, below the constant there, is the slope, negative 0.1629. You can see that the A value here is 3, that's the y-intercept, And you can see that right next to the word constant, 38257. You can see the standard error of the slope is 0.03. And you can see right there, next to the slope is the number 0.03096. That's the standard error of the slope. It also gives you the standard deviation, which is 5740.13. So it gives you all those numbers. The other numbers we don't really need right now. We just need those four kind of numbers there they'll ask you about. Usually you're going to have the computer output, so you probably won't have to do this in your calculator at all, actually. Here's the computer output. How do you start your thing? So we start with whatever your confidence level is. In this case, 90% confident. Define your variables. In this case, what is beta? It's the slope of the population regression line. We're talking about the population. Y is the price. X is the miles driven. In context, it's an F1 for a Ford F-150 Super Crew listed on Auto Trader. So then you would plan all the steps here. The scatter plot shows a clear linear pattern. So if you go back to it, you can see that scatter plot down here at the bottom does show a linear pattern. Independent, so we would need to check the less than 10% condition. Going back to the problem, there were 16, random samples, 16. There's many more than 160 Super Crews, so that's less than 10%. The normal conditions, there's no strong skewness or outliers in the residuals. Yeah, I don't see any strong skewness. There's a little bit of skewness, but not strong, and it's certainly no outliers. Equal standard deviation for the residual plot here. So if you look at the residual plot, that's the one on the right there. It does look somewhat equal, right? It looks like, yeah, about the same X and Y, above the line and below the line, pretty similar shape. And finally, random sample was used. The formula for degrees of freedom is n minus 2, I believe. So they took a sample of size 16, so the degrees of freedom is 14. If you did have to draw that, by the way, if you drew that, this peak right here would be right about degrees of freedom minus 2, so it would be at 12. The mean would actually be the degrees of freedom, so the mean would actually be 14 for this one. I don't know if they'll ask that, but it's nice to be able to draw it like that. So how do you find the t critical value? We've done that before, so this would be, I think it was 90%. So if 90 is there, there's 5 to the left. So you use the inverse t command, and you would put in 0.95, comma the degrees of freedom, which is 14. And that should give you the number 1.761. To find that 0.03, you want to take that formula, which is F over standard deviation of the sample times square root of n minus 1. So if you plugged in from your, well, we know what, let's see, we'd have to go back and look what stuff is. So usually we don't have to do that formula. Usually we can get it from the chart that they give us. Usually they're going to give us computer output. And so I would say look, again, right next to the slope. The slope is negative 1.16292. To the right of that, under SE, standard error coefficient, is going to be the number. So 0.03096 would be that number. And so you can get that and put it in there, 0.03096. You can see right here, we've got that number. We got it from the computer output. And then you can get, and just, go through and get your interval by multiplying those numbers together, adding, subtracting, and you get your interval. Finally, we are 90% confident the interval from negative 0.2174 to negative 0.1084 captures the slope of the population regression line. So that's really what we're trying to find. It's weird. We're doing regressions on the slopes. So we're hoping to capture the slope relating to the y equals price and x equals miles driven for the truck. You can also do that. Again, I mentioned that in the calculator. You can do that. I did that for you. When you see a list of data, wait a moment before typing the data into your calculator for this type of question. Usually, they're going to give you the computer output. We very rarely actually have to type this into our calculator. That's the lesson for today.